It is way too cold outside to do another opening, so instead we'll just stay inside and do some time series. Today, in our time series lecture, we'll be continuing the theory that we did with the autoregressive and the moving average process. We're going to cram them together. And what are we going to get? Well, the ARMA model, the autoregressive moving average process. We'll also look at the ARIMA model, the autoregressive integrated moving average process. And this will give us a lot more theory to understand how these tools work before we get into the actual statistics of trying to estimate and fit data to such things. So let's go take a look at that. And we're back with yet another lecture of Stat 479 time series analysis. In this lecture, we're going to continue the theory that we were doing in the previous lecture. That is, last time we went through the AR and the MA process individually. Now we're going to combine it and look at the ARMA process, and then we'll go on to looking at the ARIMA process. So we have another day with a bit of theory to get through, but after that, we'll take a little break and we'll look at some actual data now that we have sort of a new understanding of the AR, MA, ARMA, and ARIMA models. So let's get into that. Right. Well, what I'd like to do first is just kind of recap what we did last time, because there's a lot of stuff in there, and I want to make sure that we kind of remember what we did. So first of all, we discussed the AR, or autoregressive process. I should say ARP, order P. And what we learned about that is, well, first of all, how to define it. We defined it in terms of its the autoregressive operator, which is capital Phi of B applied to XT, and that's going to equal WT, white noise. So this is the sort of general form for our autoregressive process of order P. And what we found is that basically the key thing that we discovered is that this is causal in the sense that it can be written as a causal linear process if the roots, the polynomial roots, or the roots of the polynomial, well, I'm not going to say of the polynomial, the roots of capital Phi evaluated at Z for Z, a complex number, lie outside the unit disk. That is, their magnitude, the magnitude of all of the roots, let's say Ri, is going to be greater than 1. This is for all I. So what does that look like in a picture? Well, in a picture, if we imagine the complex plane, here we got the reals and we've got the, I guess, imaginary in this axis. Then what we have is we have our unit disk, approximately a circle there, and the roots should be outside of the unit disk. Maybe they're also on the other side, but as long as they lie outside the unit disk, we have a causal ARP process. If it has P terms, then it's ARP. But if all the roots lie outside, then we have a causal autoregressive process. Great. If we have roots lying on the disk, then we run into the non-stationarity issue. If we have roots within the unit disk, then we have a non-causal process. It may very well be stationary. As we discussed last time, you can have the case where the process explodes, but it's still technically a stationary non-causal process. So yeah, time series is a bit weird, right? You look at the data and you think, oh yeah, it's just watching something over time. And then you realize, there's actually a lot of crazy math going on. But anyway, yeah, so that's the ARP, the autoregressive order P process. Now, if we move on, we also discussed last time the MA order Q process, the moving average process of order Q. And similarly, this was defined to be xt is equal to capital theta b applied to wt. So really, it's the same thing as before, except we're applying the operator to the white noise rather than applying the operator to xt. In this case, we had a very similar development, but we're going to change the word causal to invertible, and that is that this is invertible if the roots of theta evaluated at some complex number z are greater than 1 in magnitude, as we just discussed with the autoregressive process. So what we have here, right, is that we have really the same setup. We're saying that if the roots lie outside the unit disk, then it's invertible. So what is invertible? Invertible means that we can write WT in terms of some type of a series. Let's see, we need, let's say, J from, I guess, 1 to 0 to infinity of, I forget what the coefficients I used. I think were they thetas? I'm trying to keep the notation the same. We'll just use, no, I don't want to use theta because theta is the actual coefficient. We'll use phi, even though I think, no, psi. We'll use psi, the little one that looks like a trident. There we go. We'll use psi j. What are we doing? xt minus j. So the idea being that we can, like we had the linear process, maybe I can write that up above here in green. So for our linear process, right, we would have xt, which is the sum of, let's say, t from, I guess, 0 to infinity. I'm going to use psi again. Not t. Sorry, what am I doing? I'm getting my indices all backwards today. We have psi I, and then we have wt minus I. So in this case, the psi's in the green and the psi's in the blue might be different values. But the point is that really, if a process is causal, then it means I can write xt as a sum of white noise from present all the way into the past, right? If a process is invertible, then I can write the white noise as a sum of the xt's of the process itself, with some coefficient going, I guess, off into the past as well. So that's roughly, and they both correspond to the same idea, which is we need these roots for the polynomial to lie outside of the unit disk. So it becomes an exercise in, I guess, complex, I don't want to say analysis, complex algebra, where you're trying to factor a polynomial over the complex numbers. Luckily, computers do that all for you, so we don't have to worry too much. But the idea that we got to last time is that when we actually want to do things like estimation, we need to know what we're estimating, and you can have invertible, non-invertible equivalent processes, and you can have causal, non-causal equivalent processes. So we have to know which one we're going to estimate, and typically the ones we want are going to be the causal and the invertible ones. And that is going to lead us into the ARMA model. So we have now the ARMA PQ model. Now, the ARMA PQ model is kind of what you think it's going to be. You're going to take the ARP, the MAQ, and you're going to cram them together, and you get an ARMA model. But we will take the time to carefully write this all out. I mean, I could just leave it at that, and say, okay, you cram them together and we're done. But it is good to write this all out in finer detail, because I know that probably you're all learning the theory for the first time. So it's really good to take some time and slowly work your way through it. I wonder if that's being picked up by the mic. Sounds like there's a sad toddler upstairs. Anyway, right, so if we want to define an ARMA PQ process, then again, we say that xt has 0 mean, which is really, again, just for convenience, as we talked about last time. We just have the 0 mean there so that we don't have to be dragging around this extra term, which is super annoying. So we assume it has 0 mean. We can adjust it otherwise. And we're going to write xt in, well, a couple different ways. The first way we're going to do it is say it's going to be white noise at current time t plus some type of auto-regressive summation in terms of the phi's t minus I. And we're going to have some j here running from 1 to q of theta j w t minus j. So now what we have here is we basically have exactly what we had before. We have the ARP piece and we have the MAQ piece. Now, we have a couple assumptions. So we have our coefficients. Oh man, we have our coefficients phi 1 through phi p and theta 1 through theta q. These are all assumed, or they're all going to be real numbers. And specifically, we want to make sure that phi p is not 0 and theta q, that's a terrible theta. Let's do that again. Theta q is also not 0, because otherwise it wouldn't be an ARMA PQ, it would be an ARMA some other order, P prime, Q prime process. So again, that's the mathematical setup, and we can also write, I'll say we also write phi b xt is equal to theta b w t. So we just take the two things that we had above here, that is specifically this piece and this piece, and then we cram them together and we get this guy here, which really just says we have an autoregressive operator, apply it to xt. We have a moving average operator, apply it to wt. And anyway, you have all these pieces. So this is what the autoregressive, or the autoregressive moving average process is going to look like. Now, there's some interesting little things that can occur. The first is going to be a problem of uniqueness, or more so, non-uniqueness. So there's a chance that, well, not a chance, if you have an ARMA model, you could actually write it in, I guess, effectively an infinite different number of ways. There's going to be the best way to write it, but the point is that, well, let's look at an example. So the example we have here is going to be that xt is going to be theta xt minus 1 minus theta wt minus 1 plus wt. So if I gave you this process, the first thing we'd look at and say, okay, this looks a lot like ARMA. I see one moving average term and one autoregressive term, so it looks kind of like an ARMA 1-1, I'll say, right? Right, when you first look at this, it looks a lot like that, but let's move some of the pieces around and see what happens. Well, in this case, if we try to write it in that form above, what we actually get is we get something that's going to look like 1 minus theta b applied to xt. And we're also going to get let's say a 1 minus theta b applied to wt. Okay, so we actually have the same operator on each side. So what we really want to do is we want to cross these out and be done and basically say xt is equal to wt. So in this case, and I should say, Actually, I should make that more precise here. First of all, cancel if theta in absolute value is less than 1. Otherwise, you can't necessarily divide by it because the power series will have a radius of convergence that is smaller than 1, so it doesn't work. But in the case that theta here is less than 1, you can cancel out both of these and you end up with just xt equals wt, and that means it's actually white noise. So it turns out that this ARMA 1.1 process that I wrote down is not really an ARMA 1.1 process. It's actually just white noise in disguise. And that's the idea that because you effectively have two polynomials, you have the phi on the left, you've got theta on the right. If they have common roots, that is, if there are common terms in those polynomials, you can feasibly cancel them out on each side and reduce the process from an ARMA PQ to an ARMA P prime Q prime for P, I guess P minus 1, Q minus 1 if you reduce it by one term. So that's another key thing, and it's a good little exercise to go through because, again, if you're trying to estimate terms in a model, right, you could try to estimate the terms and find that you just get white noise out. Or if you try to fit an ARMA 1.1 process to the same white noise, well, you might actually do that, but you're going to end up with coefficients of theta, whatever theta is. In this case, theta is not even unique. It could be any theta as long as theta is less than 1 in magnitude. So again, this makes the problem of estimation very tricky because we want to make sure that we estimate something that's in some sort of reduced form, and we want to be able to do that uniquely. So that's just one of the there we go. That's just one of the headaches that can arise when you're dealing with ARMA, an ARMA process. So basically, what I'll say is in general, I should write this out in general before we move on. In general, if theta, or let's say eta, let's say we have a to b, phi b xt is equal to eta b theta b wt, then I can cancel the etas if eta b is invertible. And I know operators like this may be a little bit new to a lot of you going through this course. But what you've probably seen, I'm assuming you've definitely seen, is some linear algebra. And you could have a matrix, right? And if, let's say, forget about operators and backshift operators, if these were just matrices, then eta could be a matrix. And if I'm multiplying on the left by the same matrix on each side of the equation, I could feasibly cancel it out. But only if it's invertible. If it's not invertible, then it's like dividing by 0 on both sides of the equation. It doesn't work. So I can't do that. But assuming that the common factors eta are in fact invertible, then I could feasibly cancel them out on both sides of the equation and reduce the ARMA model to a lower order. So again, little things to be aware of when you're dealing with such objects mathematically. All right, so what does that mean? That means, therefore, we assume that phi of z as a polynomial and theta of z are, I'll say, relatively prime in the sense that they don't have common factors, or in this case, common roots. So now we have one more condition for our ARMA process. So if we go back up, I'm just going to scroll up and not draw it again. If we go back up to our unit circle here, we want to make sure that the roots of phi lie outside the disk. We want to make sure the roots of theta lie outside the disk, and we want to make sure they don't have any common roots. So they have to have a unique sets of or a unique collection of roots. The roots have to be unique between the two of them. Yeah, you could have a double root, I guess, within the same. I want to make sure that's clear. You could have a double root or a higher multiplicity for a root within one of the polynomials, phi or theta, but you don't want to have a common root between the two of them. All right. So if all of this is true, then we have some different ways of writing the process out. So now, with the form here, that phi b applied to xt is equal to theta b applied to wt, we say that if theta b is invertible, then, well, what we can do is we can write wt as phi b divided by theta b, all applied to xt, which is going to be kind of the invertible way to write this process. That was the notation I used before, was pi. Now I remember. So what we can, no, not xt. What it's going to look like is something like xt plus the sum j from 1 to infinity of pi j xt minus j. So the idea again is that because we assume that theta is invertible, then this infinite summation makes sense in the sense that the pi's will decay to 0 fast enough. I mean, more explicitly, I should say, I can hand wave it and say they go to 0 really fast, but more precisely what I should say is that the sum of the pi's, j from 1 to infinity, I should say the sum of the absolute value is finite. So they are absolutely summable. Absolutely summable. All right. And that's going to be the property that we need here. I mean, well, that's basically what invertibility will imply. So once again, we make the claim that basically the ARMA PQ is invertible. And this is, I guess, if and only if all roots of theta, let's say z, are outside of the disk, the unit disk. And we can actually prove that, which we're going to look at in a second. But what I'm also going to do is write the complementary property, which is the causality for phi. So what I'll say is similarly, right? We say that if, how do we want to write this? I guess if phi b is invertible, we can write invertible in the sense of an invertible operator. Then we can write that xt is going to be capital theta b divided by capital phi b applied to wt, and we can write that in terms of a causal linear process, which is going to look like j from 1 to infinity of psi j wt minus j. So now what we're doing is we're saying that basically if I can divide by capital phi, if it has an inverse that makes sense, then I can end up writing out my ARMA process as a causal linear process, right? And this is where the sum j from 1 to infinity of the absolute value of the phi's, I think. Oh yeah, no, we already assumed that. Yeah, good, we're good. Is finite. So again, this is absolutely summable, which basically means the terms, the psi, the ones that look like the trident, the psi go to 0 really fast. They have to go to 0 really fast if they're going to be summable in absolute value. That way you don't have any of those issues with like conditional convergent or conditional summability if they had alternating signs or anything weird like that. We need a much stronger condition, which is they sum up in their magnitudes like that. Okay, so we have that good summability condition on the phi, or the psi. I keep doing that. All right, we're going to get through this. So what we're going to do now is I'm going to write down the result, and then I'm going to reset things, and we're going to actually prove it. So what we're going to say is that, basically, the next thing we're going to do is prove that an ARMA PQ is causal if and only if the roots of phi z are such that, I guess, Ri is less than 1, or no, not less than 1, greater than 1 in magnitude. Not the clearest of sentences, are such that R is greater than 1. But that's the idea. As long as we're going to try to show this rigorously, rather than me just kind of hand waving and saying, yeah, I can divide by phi, and then this all kind of makes sense. So we're going to do this for causality, and if you wanted to show this for invertibility, it's going to be more or less the exact same argument, just swapping phi for theta and the word causal for invertible. But we're going to take a quick break, and when we get back, we are going to prove that claim. So let's do that. All right, and we're back, and we're going to now try to prove this claim about the ARMA process being causal. So we're going to have to do an if and only if proof, which means we have to do it both ways. So the first thing we're going to do is say, for the proof, is going to be let, we're going to try to do this rigorously, let phi of z have roots R1 through RP, and they're going to be complex numbers. They're going to lie somewhere in the complex plane. So first, we're going to assume that, which way is this going to be going? This is the reverse direction. Yeah. So we're going to prove the reverse direction. Terrible arrow. Let's try that again. There we go. So we're going to prove the reverse direction first, which is to say, assume that Ri is greater than 1 for all I, equal, let's say, 1 to p, just to be precise about it. Okay, so let's assume that, and then we want to show that this ARMA process has a causal, as a representation, as a causal linear process. So let's see, how do we do that? Well, first, we say that, okay, if we assume that, then we'll say without loss of generality, W log, dot, 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 dot. So without loss of generality, assume the roots are ordered. Well, how are they ordered, right? We don't have a natural ordering on the complex plane like we would on the real line. We assume that they're ordered in their magnitude. So what I mean by that is that we have one, I guess you could define orderings on the complex plane. So I shouldn't say there is no natural ordering, but it's not as straightforward what the ordering should be. But it doesn't really matter. I'm just rambling. What we really want is we want to say that the roots from 1 to p are going to be in increasing order. So they could be equal to each other. That's why I have the less than or equal to sign. But most critically, they have to all be strictly greater than 1. So we have to make sure that they are all greater than 1, but then after that, they could equal each other. They could all be the same or they could all be different. Doesn't really matter. We just have to assume there's some ordering, and without loss of generality, they're indexed in their natural increasing order. So given this, we say let the magnitude of R1 be 1 plus epsilon. And this is for some epsilon greater than 0. Some epsilon greater than 0. So what does this mean? Well, this implies, therefore, we should say, we have that phi inverse of z exists with a power series representation, with radius of convergence. It's all about the radius of convergence here, right? With radius of convergence, I guess less than, or radius of convergence of, I guess, 1 plus epsilon, which means that, well, if I can write it out here. The inverse, phi inverse of z can be written as an infinite sum. I'm going to use the coefficient aj from 1 to, or 0 to infinity, z to the j power, the jth power. So what it means is that I can write the inverse. Remember, phi is just a polynomial. It's a complex polynomial. And if I know that the smallest root in magnitude is going to have value, magnitude, I should say 1 plus epsilon, then what that means is that I can write this inverse in terms of a power series, and the radius of convergence is going to be 1 plus epsilon, which means, right, let me just make that explicit. I'll say, i.e., if z in magnitude is less than 1 plus epsilon, then this guy converges. I guess absolutely, I believe, is the correct way to say it. Though, yeah, no, that makes sense. Okay, good. So that's basically what's going on here. Now, what do we do next? Well, okay, that's just sort of dealing with power series and complex numbers. Next, we choose a delta, where delta is going to be, I need a little bit more room here. We need to choose a delta that's between 0 and epsilon strictly. So it's still a positive number, but it also has to be less than epsilon. And luckily we have real numbers, so we can definitely find some delta that lies in between 0 and epsilon. Then choosing z to be 1 plus delta, we have that z is inside the radius of convergence. Okay. So then what are we doing with that thing? Well, what we're going to do is we're going to plug it into the series and we're going to move some terms around to see what happens. So let's scroll this up. We'll say, therefore, if I evaluate my polynomial phi at 1 plus z, or not 1 plus z, at z, which is going to be 1 plus delta, because that's how I chose it to be, then what I end up with is something that's going to look like the sum j from 0 to infinity of aj 1 plus delta to the jth power. And because it's within the radius of convergence, we know that that sum is finite. We don't know what it is, but we know it's finite. So that's all that really matters for our purposes now. Because again, what we're trying to show is that our ARMA process has a representation as a causal linear process. So that's what we're kind of fighting our way to through all of these derivations, which means ultimately we want to show that something is summable. Right, so what do we do next? Well, because this thing is summable, we say, therefore, there exists a C, a constant greater than 0. This is some constant. So there exists a constant C greater than 0, such that these coefficients here, aj 1 plus delta to the j, have to be less than C. Right, remember this series here is convergent. That means that the terms, the summands, I believe is the right word, the terms in the series have to get smaller and smaller and smaller. They could get big they could get large in a finite sense and then decay. But in the long run, these terms have to go to 0, or else we're not, and they have to go to 0 pretty fast, or else this thing is not going to sum up, is not going to converge. So all we're saying is that because we know that this series converges, we know that there's going to be an upper bound. This infinite series of coefficients, or this infinite sequence of coefficients of terms in the series, has to have an upper bound. We're going to define that upper bound to be C. Or it has to have just some upper bound. It doesn't have to be like a sharp upper bound by any means. And this is, I should say, for all J. Okay, so now that we have that, we just rearrange the terms slightly, and we say, once again, I'll do 3 more dots and say, therefore, and therefore, we have that the absolute value of aj is bounded above by C, 1 plus delta to the minus j. So what we have here is we have an upper bound on how fast, or how, I guess, an upper bound on how slowly the AJs can go to 0, and they have to go to 0 in this geometric fashion with a rate of 1 plus delta. So what this is telling us is, just how fast or slow the AJs go to 0. So that's what we're really doing here. We're saying because this series is this sums up, it has a finite sum. We know that the AJs have to go to 0 at a certain rate, at least at a certain rate, because otherwise it wouldn't make sense. So what does this all mean? So all of this implies that, well, what? It implies that we can take our ARMA model, which is going to look like this. And what we can do is we can rearrange the terms to get something that's going to look like xt is going to be equal to phi inverse b theta be wt. And what that means is that we can actually write this out as a causal linear process in this form. Phi j wt minus j. And as the AJs are absolutely summable, I'll say so are the psi j's. Because you can actually write the, can we do that? Is that going to be a pain to do? Let's see if we can actually do that. You should be able to write the psi j's in terms of the AJs and the thetas, right? Because I think if we go all the way back to the beginning, the AJs at the top of the screen here are going to, they're going to be the coefficients for phi inverse. So what we're basically saying, let's write that out just to make sure. We got some time, so let's write that out. What we're saying is that if we have something like phi inverse of b theta b, then what we're really saying is that we have, well, the product of two sums. We have a sum here, j, from, I guess we were going 0. Let me double check. Yep, 0 to infinity. Sometimes it's 0, sometimes it's 1. It's always good to double check to make sure I don't get that wrong. So we're summing aj, bj, or b to the jth power. And then we have, I think I might have switched my indices, but that's okay. I from, I guess, 0 to, or not infinity, no. 0 to q of theta I b I. So if we were to combine these together, well, it's going to be kind of annoying to work out what the terms are, but you're going to get some type of summation. I guess we can say j from 0 to infinity, I from 0 to q, and then we're going to have a coefficient of aj theta I, and then bj plus I. Right. So we have something like that, and if we really wanted to, we can write this. I don't really feel like trying to define exactly what phi is, or psi is, because it would be kind of annoying to do so. But yeah, the point is that we can write it out like that. Since there's only a finite number of thetas, it doesn't really matter. I guess the easiest way would be to just fix a theta and then sum up, know that the A's are summable to infinity, or absolutely summable, so we're all good to go. Anyway, that's the first half of the proof, right? Which basically says if the roots lie outside the unit disk, then we have this causal representation of our ARMA process. Let's do the reverse now and see how that works. So for the reverse, it's actually the forward version of the proof based on the way I wrote the statement above. So now we're going to do the same thing, but we're going to do the, I guess, the other side of the if and only if. I always forget which way's if and which way's only if. It linguistically never really made a lot of sense to me. Anyway, yeah, so what we do is we say let phi of b x t equal theta b w t b, and ARMA PQ process that is causal. Okay, so what does that mean? Well, that means exactly how we ended the last proof. I'll say that is, we can write xt to be the sum well, I guess what I'll do is I'll take out the WT first. It'll be WT plus the sum of, we'll say J, I'm using J, yeah, from 1 to infinity of psi J WT minus J. So there's our causal process. Now, what we want to show is we want to show that if this is true, then the roots of phi, I'll write that down just so it's clear. Want to show that the roots of phi are outside the unit disk. I often forget what I'm actually trying to prove when I'm going through a proof like this, so I'm always have to remind myself, what are we actually trying to do? So we start with the causal process. We want to show that the roots of phi lie outside the unit disk. Okay, so how in the world do we do that? Oh, one other thing I need to say, that is this, with the psi j from 1 to infinity, the sum from 1 to infinity of psi j being finite, or again, absolutely summable, right? That's the only way these things make sense, is if the coefficients decay fast enough, as they do by assumption here. All right. So that means we basically can do two things. Well, we write, two things. We write that xt is going to be what? It's going to be capital psi b of wt. This is, say, causal linear process. And we can also write phi, capital phi b, xt equal to capital theta b, wt, which is ARMA PQ process. Okay, so now that we have both of these, well, we can actually kind of plug them into each other and see what we get out, right? And what we get out, double check to make sure we got this right. Yep. Okay, good. Therefore, if I let me move that. Therefore, if I combine the two of these, what I end up with on the left is I get a phi b applied to a psi b applied to xt. And on the right-hand side, I just have my capital theta b applied to wt. So if I take these two and I combine them together, I get this thing. Okay, so where's that going? Well, if we write phi z, do I want z? Yeah, I want z. Psi z to be the sum, I was using in this case, from 1 to infinity of a, oh, I did mess up that index. I need to fix that as well in the notes. J from 1 to infinity of aj, z to the j. Then this has a radius of convergence that is greater than 1. Okay, so y, well, I guess it could be greater than or equal to 1. Or is it greater than 1? No, I think it's greater than or equal to 1. Yeah, all the, yeah, no, because if it's equal to 1, then the root would have to lie outside. It doesn't, no, I'll just say greater than 1. That's fine. We don't, yeah, it doesn't really matter. So all the roots are going to be outside of the unit disk. So there's always going to be some 1 plus epsilon there. So it doesn't really matter. Anyway, yeah, so why is that true? Well, it's true because we know that psi the coefficients psi are absolutely summable, and phi is a finite polynomial. So right, this I'm running out of this polynomial this is a finite poly, and this guy is absolutely summable. So when I multiply the two of them together, kind of like what I was trying to do up here in blue for phi inverse and theta, the same thing applies down here. If I have a finite polynomial in Z and I multiply it by an infinite power series, but with absolutely summable coefficients, then I know that I still get something that's summable. And if the radius of convergence is greater than 1 for phi, then it's going to be greater than 1 for phi times for psi. If the radius of convergence is, these Greek letters, I tell you, right? If the radius of convergence is greater than 1 for psi, and then I multiply it by a finite polynomial phi, then I'm still going to have a radius of convergence that's greater than 1. Whew. Almost going to made it through this. So I'll say, hence, we can write, well, the point is I'm going to take this thing here. If that arrow is, yeah, that arrow kind of made it. Good. Hence, what we can do is we can write this as the sum. Then we're going to have two things here. We're going to have j from 1 to q of theta j, wt minus j, and we're going to set that equal to the sum j from 1 to infinity of aj, wt minus j, right? Because that's just that equation up above that I have the big green arrow kind of snaking around to get me to. And what it's telling me is that, well, I have two different series in terms of white noise, and they are both equal to each other. So what does that mean? Well, the short answer is, therefore, aj is equal to theta j if j is equal to 1 to q, and aj has to equal 0 otherwise, by matching coefficients in that thing. Okay, so that kind of makes sense intuitively, right? If I have two series in terms of white noise, I have certain coefficients on one side, I have certain coefficients on the other side. It seems intuitively to make sense that I might want to try to match them up. Why is that true mathematically, right, is the question we should be asking. It's true mathematically because we can compute the covariance of these two between these two terms. So I'll say this makes sense mathematically by computing covariances and noting that the WTs are uncorrelated. So there is an actual mathematical reason why it makes sense to do that. You can, I guess a better intuition would be to note that all the W's, the white noise pieces, are uncorrelated. So if I have a WT minus J that has a theta in front of it, and I have a WT minus J with an A in front of it, it turns out those things have to be the same because all the other terms are not going to, in some sense, interact with it in the sum because they're uncorrelated. Now, mathematically, we could actually just write this out without trying to hand wave it with intuition in terms of computing the covariances, because if we actually were to compute the covariances here, then we would find out very quickly that we'd have a bunch of linear equations, and that the only way it makes sense is to have the thetas and the a's equal to each other given the same index. And then, of course, all the subsequent aj's being 0. Okay, so what does all of this mean? That means, therefore, so finally, we have that, where is it? Capital theta, the polynomial in Z, just happens to equal capital phi Z, capital psi Z. Cool. And this is, I should say, for Z within the radius of convergence, but we'll just say less than 1 because we know the radius of convergence has to be at least 1. Well, I guess I can say less than or equal to 1 to be precise. So therefore, since none of the roots of psi lie within the disk, by assumption, right? We started this entire second half of the proof by assuming it's a causal, it's a causal process, which means that its roots have to lie outside the unit disk. So we know that that's true. I'll say then, if there is I think I used Z naught inside, or I'll just write in the disk, such that phi, it is a root of phi such that phi of Z naught is equal to 0, then, well, what does that imply by this equation here that I'm about to, if I can do that, underline in green? Well, what it implies is that then, not in green, it implies that theta Z naught is also 0, therefore they have a common root. And this is not, and therefore not, an ARMA PQ process. And that's where we get our, I guess, contradiction or our problem here. Since we want to assume, we assumed initially that we had an ARMA PQ process, and oh yes, there goes the camera. Well, I'll just finish the thought process and then we'll reset for the last bit. What I was saying is that because what we do is we assumed that we had an ARMA PQ process, they shouldn't have a common root. And the only way that a root would exist within the unit disk is if there was a common root among theta and phi, and we would just cancel it out. Therefore, that's not the case. We'll say, therefore, all roots outside unit disk. And we can put our little box there and be happy, QED. Okay, so there was the proof that if we have a causal ARMA process, then the roots of the autoregressive polynomial phi have to lie outside the unit disk, and that's if and only if. So if the roots lie outside the unit disk, we have a causal process. If we have a causal process, the roots are outside the unit disk. Now, the exact same thought, the exact same proof in some sense would work if we wanted to determine if the ARMA process is invertible in terms of using theta. Now, it would be the exact same proof, except we'd be swapping the roles of phi and theta, but really everything would be exactly the same. So we're not going to go through that, but if you want to work through it yourself just to see if you understand how this proof works, that's always a good exercise. For the final piece of this lecture, what I want to do is talk about the ARIMA process. So we're going to go one level deeper into this, and then we'll finally have all of our building blocks for the ARMA, ARMA, ARIMA processes. And then we can actually do some statistics with this, perhaps. So, like I said, stick with me here because this stuff is kind of dense theoretically, but we will eventually get back to statistics. So don't worry, you got to trust me on that one. Right, so before we end this lecture, we still have some time left. So let's talk about the ARIMA process. All right, so what is the ARIMA process? Well, the idea is that, so often, I'll say, often XT from wherever XT is coming from, whether it's your stock prices or your COVID cases, your daily temperatures or whatever, often XT is not ARMA PQ, but is ARMA, is ARMA PQ, comma, P, comma, Q with a deterministic trend. So what do I mean by that? Well, what I mean is that we might actually have, I think I was using W or Y, so I'm going to switch XT to YT. For example, e.g., we could have YT equal to beta naught plus beta 1T plus XT, where XT is ARMA PQ. All right, so the idea is that in practice, we very often have some type of a deterministic trend that is the mean of our processes changing, like some polynomial. The most typical one would just be linearly, like I wrote down here. So we have some beta naught, beta 1, and we have that there's a line, and then there's some time series fluctuating along that line. I should say a stationary ARMA process fluctuating above and below that line. So then the thought process is, if that's the case, then if I were to take a first difference of YT, something that we kind of did in the first assignment, or you kind of did in the first assignment, then what you end up with is something that's going to look like beta 1 plus XT minus 1. So we basically lose the constant term beta naught, and then beta 1 goes from being a slope to being like a constant term. And this is now stationary, and it happens to be, I guess, some ARMA process. Strictly speaking, I don't know off the top of my head if it's going to be ARMA PQ. I'd have to think about that for a second, because we have XT minus 1. So the terms could, odd things could happen if you take the terms, you offset them by one time unit, and you start subtracting them. But we're not going to worry about that for this example. The point is that we would be back in we would have some type of ARMA process. Of course, there would be a non-zero mean, which would correspond to beta 1, or something like that. Anyway, this gets into the idea of the ARIMA process, or the auto regressive integrated for I integrated moving average process. moving average process. So I never really, interesting why they would say integrated. I assume they mean integrated because we're actually going to be applying a first difference operator d times. So if we were to, in some sense, undo the differencing, it would be like we're integrating to get the process that we are studying. But effectively, the intuition is that if we keep applying some differences, we'll eventually get down to a stationary ARMA process by differencing out the trend, however many times we have to do a difference. If it's linear, we do one difference. If it's quadratic, we do two, and so on. If we're dealing with real data, even if it has a higher power trend, probably one or two differences would be enough to kind of kill out the trend anyway. So what are we doing? Well, what we're going to do is we're going to say, recall that delta D is going to equal 1 minus B to the D is the dth order difference operator. There we go. So we have that thing, and we can apply it to, I guess, xt. So the thought process is that xt is ARIMA PDQ if delta D xt is, I guess, ARMA PQ, yes. So that's the setup. The idea is that we actually want to do D differences, and then after those differences are done, we're left with an ARMA PQ process. So mathematically, what does this look like? Well, what this looks like is going to be, well, in terms of operators, we're going to have phi of B, the autoregressive piece. Now we're going to have a delta, or I guess a nabla, the upside down triangle, to the dth power applied to xt. And we're going to have our moving average piece here, theta B, applied to the white noise. So now we have the integrated, so the autoregressive integrated moving average pieces, ARIMA, spells ARIMA. All right. So in this case, again, we can assume zero mean. I guess we can work through that just to show what happens, because there's not really much more to tell you about the ARIMA process, except that we're doing these differences to get rid of any sort of deterministic trend. So very often in statistics, when we're looking at time series data, we'll want to take a first or a second difference to get to a stationary process and then fit an ARMA model to it. Or you can use the nifty function auto.arima, which will just do it all for you. And we'll, of course, talk about all of these things in later lectures. But for now, I'm just going to talk about the mean, and then that looks about enough for, I think, a good, solid, tedious theoretical lecture. So I'll say we assume, for convenience, if I'm spelling that right, which I'm pretty sure I'm not, that the dth difference of xt is mean zero. And I'll say, if not, then we can kind of work our way backwards and shove a mean into this equation. If not, we have that phi, capital Phi of B, applied to, well, maybe I'll just write it out as 1 minus b. This is just the differencing operator written in terms of the backshift operator. Sometimes it's nicer to look at it that way. Anyway, we have that. And then we're going to have two pieces on the left-hand side, or the right-hand side, sorry, the right-hand side. We're going to have mu 1 minus the sum I from 1 to p of phi I. And then we're going to add to that capital theta b applied to wt. So now we have our mean here. And yeah, the idea being that if we sort of difference this out, then we would have, I guess, that mean still in the equation. Yeah, I'm not sure. There's nothing too much more, I think, to say about this right now. Right, so I think that's more or less what I'm not going to keep rambling on here in front of the camera. Effectively, that's all we really need for the autoregressive integrated moving average. Everything that we did before kind of can just translate through to this thing. So we talked about the AR, the MA, and the ARMA process. The ARMA process has two key pieces to it, or two key properties, and that's going to be the causal representation and that it's invertible in the sense so that the moving average piece is invertible. And then what we'll want to do is we'll want to consider the ARIMA process, which is really just the same thing, but in some sense integrated by throwing on some deterministic polynomial trend. Because now mathematically what we end up doing is we end up differencing out that trend. And then we can, after differencing it out, we would end up trying to fit coefficients to the ARMA process, the ARMA PQ process, and all of the same things would translate through. We would want to have an ARIMA process that has that causal and invertible representation. This is really important for estimating the terms because it's going to mean that the terms in our model will be unique and we have a nice way of actually writing them down because, again, there's so many different equivalent ways to write down these models mathematically. We need to make sure we only have one way to write them down so that that's the thing we're going to estimate. And at least in this case, if we restrict it to being causal, we restrict it to be invertible and all that, and we restrict the ARMA to be irreducible in the sense that we don't have the same roots on the left-hand side and on the right-hand side, then we have something we can actually work with statistically. And that's what we're going to do in the next lecture or two. I think in my notes, the next thing I'm going to talk about is autocorrelation and partial autocorrelation, but I think it might be nicer just to jump in and actually show some examples of the ARMA and the ARIMA process first, and then we'll get back and do some autocorrelation, because again, this whole course is basically ARMA and autocorrelation, and a little bit of other stuff along the way. So anyway, that's it for today. See you in the next lecture.